Hello everyone, this is your tutor AB. Today we're going to be solving a problem from the IB Physics HL May 2024 examinations. This is a paper 2 problem. Let's get started. An object attached to a spring oscillates with simple harmonic motion in a horizontal plane. The graph shows how the kinetic energy of the object varies with the displacement x. Okay, so here we have a graph to represent the situation. So part A, state the amplitude of this motion. Now, the amplitude is basically just the difference in displacement from the equilibrium position to either the maxima or the minima. So in this case, we can take from either the positive side or the negative side, but the magnitude would just be 6 centimeters. This essentially, if I were to draw like a small pendulum, would be something like this. So this is the equilibrium position right here, and this is the maxima. So this displacement right here, going from here to this equilibrium, that's its amplitude, and that's what this half graph represents. That's the 6 centimeters. So 6 centimeters. Okay, draw on the axis above the variation with x of the potential energy stored in the spring. So the idea is that the kinetic energy and the potential energy are exactly opposite of each other. So for example, at, let's say right here, at this position right here, this is a kinetic energy graph, right? Kinetic energy. So this point right here represents this maximum position. So at this maximum position, you have minimum kinetic energy. So zero kinetic energy because your velocity is zero. But here is when you have the maximum vertical displacement. So here you'll have your maximum potential energy. So you'd be somewhere there. And what happens is that you're exactly opposite. So whenever you have maximum kinetic energy, you have minimum potential energy and vice versa. So it's exactly opposite of the kinetic energy graph. It's just flipped. Okay. Now explain how many times during one oscillation the kinetic energy of the object and the potential energy stored in the spring are equal. Now this is slightly a trick question, but it's not too bad, and I'll tell you why. So here on this graph we can see exactly 2 points when both the kinetic energy and the potential energy are equal. But what you need to understand is that this is just one swing. So on a pendulum, right, because this is a simple harmonic oscillator, one full oscillation is you go to this position and then you go back to the original position. This going back and forth motion once is one period. Now what this graph represents is just going to this position. It needs to come back. So to go from the leftmost position to the rightmost position, there are 2 points when your energies are equal. So coming back, there are 2 more points. So in total you have 4 points. Right, so you'll have like twice in this middle position right here, and again twice in this middle position. So you have 4 points in during one oscillation where your kinetic energy and potential energy are equal. So you have 4 times during one oscillation, or you could say oscillation, or you could say 2 times during a half oscillation. That would be the right answer for this question. Okay. Now, part D. The mass of the object is 0.15 kilograms. Show that the period of the oscillations is about 0.7 seconds. Now, if I go upwards, we know this is a spring system, spring mass system. So in your data booklet, for topic C, you have one equation for the period, which is T is equal to 2 pi the root of m over k, where m is the mass of the mass and k is the spring constant. Now you can see 2 pi is a constant, m is a constant because we're given it here, right? We're given it here, and we just need to simply solve for k. Now how do we solve for the spring constant? Now what does this graph tell you? The graph is an energy graph. So do we not have an equation that helps us relate energy? We have in topic A, we have a helical energy, EH, or this is just the same as kinetic energy for springs, which is half K delta X square. Now this is in your topic A of the formula booklet. Now we can basically rearrange this to solve for K. And now we know what is the helical or kinetic energy of a spring because we're given it in this graph. The maximum kinetic energy of the spring is basically 20 millijoules. So we can basically equate them. So we can say 20 millijoules, which is 20 to 10 to the power of negative 3 joules, is equal to half K. And what's the delta X square? Now, the amplitude is basically 6. So we know that the delta X is also just 6, right? That's the amplitude. X represents the amplitude. So instead of 6 centimeters, we need to convert it to meters. So that's basically 6 into 10 to the power of negative 2 the whole square. And now that's meter square. That's in the form of meter square. Okay, now what do we do? Now we need to rearrange for K. So we can say 40 into 10 to the power of negative 3 over 6 times 10 to the power of negative 2 the whole square, that's equal to K. Now we can directly plug this into this equation. So T is equal to 2 pi. We know M is 0.15 and we know K is 40 into 10 to the power of negative 3 over 6 into 10 to the power of negative 2 whole square that. Now see what that value gives us when you put it into the calculator. So 2 pi the root of 0.15 over 40 into 10 to the power of negative 3 over 6 into 10 to the power of negative 2 the whole square. That gives you 0.73 seconds. Okay, and that's approximately equal to 0.7 seconds. So we've solved this question. Now, finally part 2 of this question. Calculate the maximum force exerted on the object by the spring. Now, we know a formula for force directly, which can basically remove lots of the working time, okay? And that's the force of a spring. The force of a spring is basically equal to F equal to K delta X. Now, we solved for K earlier, which is with this term right here. So we can just directly say 40 into 10 to the power of negative 3 over 6 into 10 to the power of negative 2 the whole square. And this times by the amplitude, the delta X. And delta X is basically 6 centimeters. So that's 0.06 meters. Okay, now if I just equate this to F, we can find out what's the answer. So F is basically equal to 14 to 10 to the power negative 3 negative 2 the whole square. We get 0.667 newtons. So that's basically like 0.67 newtons. Okay, thank you for watching. Please like and subscribe. If you have any questions, leave it down below and I'll answer it as soon as possible. Thank you for watching.